Speaker is Sebastijan, talking about bisimulations for generalized Veltman semantics.
Hi everybody, welcome to my second talk today. The topic of this talk is N bisimulations, and of course bisimulations for generalized Veltman semantics. And unlike the previous talk, in this one we will focus only on generalized Veltman semantics. So this presentation is structured as follows. After a brief introduction, and also I changed my pen to red, we will define model N equivalence and N bisimulations, and of course equivalence and bisimulations for the case of generalized Veltman semantics. Then we will show the standard results that N bisimulation implies N equivalence. And then in order to show that the converse is not true, we will show how to convert Veltman models into generalized ones. Since there are well-known Veltman models with two model equivalent words in them that are not bisimulated, we'll try to try that counterexample for usual Veltman semantics, turn into a counterexample for the case of generalized Veltman semantics. And in the process, we will develop some useful constructions, for example, games on generalized Veltman models. And at the end, we will comment some future work. We will assume that you're familiar with these concepts: interpretability logic IL, Veltman frames and Veltman models, generalized Veltman frame. And as I mentioned earlier today, generalized Veltman semantics is important since Veltman semantics is not fine-grained enough for certain applications. In 1990s, the notion of generalized Veltman semantics emerged to obtain certain non-derivability results. And it has turned out that this semantics has various good properties. And the idea of generalized Veltman semantics is that we use sets of words, like here. Let me just skip to the case where we define in the definition of for singulation. When this formula A interprets B, true at the state W in generalized Veltman model N. If for all words U, which are L successors of W, and this first A is true at them, then there exists, and now this is set, such that it is SW, so now SW relation is relation between words and sets. And on this set, the formula B is true. That means that for every B in this set, B is true on that word B. Okay. So first, to define model occurrence, we need to define model depth. And that tells us how much of model can a formula see from the current state. And that obviously depends on how deeply the modalities it contains are nested. For example, if we consider this formula, then model depth of this formula is equal to 2. And even if we put here our modality, that is still 2 because of this maximum. Okay. And I should probably point out that we will deal with the case of generalized Veltman semantics, while the case of ordinary relational Veltman semantics for interpretability logic was done here by Veljan Čačić and Domagoj Vrgoč. in paper called A Note on Bisimulation and Model Occurrence in Probability Logic and Interpretability Logic. Okay. So model logicians are interested in when two worlds in two models are not indistinguishable or indistinguishable by model languages. That is, when do they satisfy exactly the same model formulas? And we will see that they are modally equivalent. Oh, that will be later. We'll make a connection with bisimulations, but also we'll be interested when they are modally n for some natural number n equivalent, and for number 0, we'll say they are propositional equivalent, because then it's enough that they agree on same propositional variables. And n equivalent means that we only consider formulas which have depth less than or equal to some number n. And the intuition is that in a sense they are same if we are not looking beyond some n horizon. So if we just look up to some n and not outside, they are equal. Okay. We'll define n bisimulation for generalized Veltman models. n bisimulation is a natural way of finitely approximating bisimulation, and in model logic, that these finite approximations are crucial for the search for finite models. So let's take a closer look. We have a sequence of n+1 relations that are all subsets of this relation Z0. And if we look at atomic condition, we see that all of them, so this means that for all Zi, this thing should hold, so that they are, as it's said on this slide, they are propositional equivalent. So they satisfy the same propositional variables. So propositional variables cannot distinguish them. And the most interesting case is this fourth condition. And we will only comment on this condition and not back condition, because there is an symmetry between them. And it's probably easier to look at this picture. And here I will show you why the definition is just like here. And here said for every I from 1 to n, this means for every this z with index from y to n, because on z0 we only need this condition. For every u such that w are u, and these are shown in picture. I will not just read to you. We want to show that this theorem holds. So if they are n bisimilar, then they are n equivalent. So no formula that has depth less than or equal to n can distinguish them. So, and that is by easy inductive proof on complexity of formula f. So if here holds f, then it should hold here. So in the case that we have formula that f is formula A interprets B, the fourth condition is used in a way that we assume here that this formula is true, and we ask ourselves, is it true here? So how should we show that here this is true? Well, exactly by the definition on this slide. So for every R successor, and this is this U that A holds on, we should find some set that is SW related to him, and in which every V is related to this V prime. So if he holds B, then he holds B, like in definition here. So for every element of this set, B is true. So if we take an arbitrary U that A holds on, then by fourth, there exists this U prime that is R prime related to W prime. And now, because this is true on W prime, there is, for every S prime W prime, we have this V primed. And again, by fourth, we have this V. And also by fourth, there exists V. And for every V in V, there exists V primed, which is shown here by this dashed line. And since this holds on this V, B is true. And by hypothesis of induction, B is then true here. So everything works because this definition is set up so that this theorem could have an easy inductive proof. And now we will, for the most of the rest of my presentation, we'll try to show that the converse does not hold. Or more precisely, we'll try to get somehow two generalized Veltman models and show that they contain two worlds that are modally equivalent, but not bisimilar. And since there are well-known examples, like here, for the usual Veltman semantics, that is two Veltman models with two worlds that are modally equivalent but not bisimilar. We'll try to somehow convert them to generalized Veltman models with two worlds that are modally equivalent but not bisimilar. So, how to, from Veltman, usual Veltman models, obtain generalized Veltman model? And you see, it looks like they're the same, but they're not, because this is relation between word and set, and this is relation between word and word. And we'll define it like this. So when we will word be SW related to some set of words, if and only if there exists some set, I can show that like here. Okay, if there exists, that only exists, not forever. And the reason because of that is that this should be generalized Veltman models. So we have a list of properties, a finite list of properties that must hold. And for instance, one property is that if some V is in this relation with some set, and this is subset of some set Z, for instance, okay, Z, then it should be the case that this holds. And this is obviously true if we define it like this. And all the other conditions are easily checked. So, and of course, if we left out this part, then we just have a frame. So for now, we can this Veltman models convert into generalized ones. But that's not enough, because here these words are modally equivalent, but they are not dissimilar. So how can we guarantee that when we make this transformation, that the word which will be transformed in this one, and this word will transform in some other word? How can we guarantee that these words are still modally equivalent, but not dissimilar? So obviously, we should prove that this transformation preserves model equivalence. So I just comment that it is checked that this is really a generalized Veltman model. And by induction on complexity formula, we can prove that if for every formula f, if that f is true on this word in Veltman model, then when we make this transformation and obtain generalized model, this word will also make f satisfiable. That means they are in some way equivalent. Okay, here's just the simulation instead of sequence. Now we have just one relation, and this is all like before, but we are not. Here is not z0. Here is not zy. It's only one relation set, because there are these parentheses, which means that this is not only the story of preservation of n bisimulation, but also the preservation of bisimulation. Okay, so the only thing that's left, so the model equivalence is preserved, and now is the bisimulation or n bisimulation also preserved, and this theorem says yes, this is for bisimulation, but the same thing is with n bisimulation. So if we have two words that are from this side or that are bisimulated, then when we convert these models into generalized ones, the bisimulation is preserved. Okay, so this is the standard usual counterexample from the book Model Logic by Blackburn, Derricke, and Panama, which shows that necessity of finite image property in Hennessy-Milner theorem, but in GL and Veltman models, this is not good enough, because this relation is not conversely well founded, because we have an infinite chain of words that are related. And in the mentioned article by Bernard Jaish and Domagoj Vuković, they have constructed two GL models that have these roots, W1 and W2, that are modally equivalent but not bisimilar. And they, so these are, more precisely, these are GL models, and then they have converted them in Veltman models by this definition, where this is a reflexive closure of R. And then they showed that this, and now they are just Veltman models, these words in them are model equivalent but not bisimilar. And we have here just a second. Showed how to define generalized Veltman models from Veltman models, and we have here two Veltman models, so that the model equivalence and bisimilarity are preserved. So again, these words before are model equivalent but not bisimilar, and that is the proof of and that is the counterexample that the converse of the theorem doesn't hold. So for games, the notion of game for cryptic models was defined by Valentin Goranko and Martin Otto from Handbook of Model Logic, and the notion of game for Veltman models, as mentioned, was defined by Veran Čačić and Domagoj Vrgoč in their paper. And in my last talk, I defined bisimulation game for generalized Veltman semantics. Just a quick reminder, we have challenger and defender, and they move from one configuration to another. So every configuration is basically a pair of sets from each, a pair of worlds from each model. And this is all that all was in my first talk. So maybe just take a look. Okay, challenger is first one, and he chooses one model and then makes move in that model, and defender has to respond with a similar move in the other model. And the difference between games for usual Veltman semantics is that we have again sets, and defender and challenger must pick sets and not just one vote. And the key difference is when they have picked these sets, the question is from which states does the next round go? So if they here picked U0 and U1, so if that's okay, but if this set is picked, then the challenger chooses which role from this set. And in case the challenger has chosen some vote from this set, the defender must respond by some vote from the other set that was picked, and then the next round is played from this configuration. And that makes sense if you look here. Here we said that for all V, there exists some V prime in another set, and that's basically the main idea between this, whichever vote does challenger pick, there has to be a vote in the other set that is good enough. Remark as before, an end game is when we restrict ourselves to n rounds. And if challenger hasn't won, the defender wins and game ends. A zero game is just to check that these votes at the beginning of first round are propositional equivalent. And these steps 5 and 4 can always be played because one hand defined, because of quasi-reflexivity, this set as just one vote, V, or here, VI. Okay. And there is a standard result that every bisimulation game ends because, as we saw here, we don't want infinite chains, because then our relation R is not conversely well founded. So this cannot happen. And some results are in these articles for IL and GL. And to conclude, there is also a proposition, like in a case of IL, GL, and the basic model logic. And that is that defender has a winning strategy in some endgame. if and only if these two words are n bisimulated. And that's all, folks. So thank you for your attention.